Now we're going to look at the trig ratios as functions. And we have to talk about what kind of functions they are first, because they are special kinds of functions called periodic functions. And a periodic function is just a function that has one set of points that repeats in a certain interval of time, and that certain interval of time, or interval of the x value, is called a period. So here's the formal definition. F of x is periodic if for some positive constant p, f of x plus p is equal to f of x. All right, now the smallest value of p is called the period. It's the smallest chunk of the graph that you can take and then repeat to generate the entire graph. Now thinking about sine and cosine, they're also referred to as circular functions because they are generated by going around and around and around in a circle. And since circles have 2 pi radians, I know that the sine of theta plus 2 pi is going to be exactly the same as the sine of theta. You know, it goes back to that whole reference angle thing and coterminal angles. These angles are all coterminal, so they have the same sine value. Same thing here. If I have cosine theta plus 2 pi and cosine theta, those are exactly the same because those two angles are coterminal and they'll have the same value, which is why we have a periodic function. In addition to being periodic, one is even and one is odd. And we're going to assume that xy is on the unit circle. X is equal to cosine theta and y is equal to sine theta. And you'll notice that I have theta and negative theta. And if I think about the cosine of negative theta, which is the x value, right, it's exactly the same. So the cosine of negative theta is exactly the same as the cosine of theta. If I think about the sine of negative theta, the y value, well, they're opposite. So in this case, the sine of negative theta is negative sine theta. And what does this have to do with even and odd? Well, it happens to be the definition of even and odd. If a function with a certain domain has this property where if I plug in the negative value of x and it spits out the exact same function, f of x, with no change, then therefore it is an even function. So with that, cosine is even. And odd functions is when I plug in f of negative x and the resultant function is the opposite of f of x. That is an odd function, so therefore sine is odd. Okay. Now a function doesn't have to be even or odd, it can be neither if it wants to. Well, for us in the trig graphing section of Algebra 2, it all has to do with the graphs. Because even functions will be symmetric with respect to the y-axis, like good old-fashioned y equals x squared. So if I have some point xy, I'm going to have the point negative x comma y with it. And then an odd function is going to have a graph that's symmetric with respect to the origin, like good old-fashioned y equals x cubed. If it has the point x comma y, then it's also going to have the point negative x negative y. So then cosine is going to be even or symmetric with respect to the y-axis, and sine is going to be odd or symmetric about the origin. So now let's look at a piece of the graph of sine, basically the part of the graph that goes from 0 to 2 pi, which happens to be the period of the graph of sine. I know it's 2 pi, I know it's odd. And just by using key points, and a key point is an intercept, like an x-intercept or a y-intercept, and the minimums and maximums of sine. And if I just graph from 0 to 2 pi, I get a little curve that looks like this. And since I know this function is odd, that means I know that this function is going to continue on this way, going down and then up and then back down. And if I extend this to be all reals, then of course I'm going to have the telltale sine wave. Now if I look at the graph of cosine from the interval 0 to 2 pi, because remember that's the period, it's an even function, and this graph, using once again intercepts and max and mins, starts up here at 1, goes down, and then comes back up. And since it's symmetric about the y-axis, it's going to go back down and mirror along this other side. Now, the primary difference between a standard sine and cosine, of course, is the fact that they're even and odd. And actually, if you just imagine me shifting this function pi over 2 in this direction, it's going to look just like sine. And if I shift this function pi over 2 in this direction, it's going to look just like cosine. Another little thing about notation with trig functions, if you see y equals 2 sine x, that's exactly the same thing as 2 times the sine of x. Now, when it comes to the graphs of the trig functions, we are going to stick with just sine and cosine. I am going to leave tangent to your pre-cal teachers. So this is a general form of a sine equation, and this is a general form of a cosine equation, y equals d plus a times sine, open parentheses, bx minus c. Each of these, a, b, c, and d, have an effect on the graph, and that's what we're going to talk about in this section. So first thing, just remember your transformations, and I'm going to actually use our concepts that we learned earlier with transforming equations by just manipulating by multiplying and adding to figure out what a, b, c, and d do. So first we're going to talk about a, which is probably the most important part of the transform function because it corresponds to something called amplitude. And amplitude is 1/2 the distance between the maximum and the minimum. And in terms of transformations, it's the vertical stretch or shrink. So it's taking the sine and pulling it apart or squishing it back down. And if I just have y equals a sine x, y equals a cosine x, the a is the amplitude, right? So this thing that I multiply sine or cosine by on the outside, that's the amplitude. And if you think about like quadratic functions, like when I had y equals x squared, if I took that and I multiplied it by 3x squared, then it would stretch it and make it vertically and make it skinnier, right? Same thing here. That's what amplitude is going to do. Now, if a is negative, it's the same thing as if it were y equals negative 3x squared. It's just going to reflect it through the x-axis. Now, something that's new for periodic functions is what this b does when I multiply x times b before I take the sine of it. And that is actually going to relate to a horizontal stretching or shrinking, which means a lengthening or a contraction of the period, because the period is normally 2 pi, but when I make it bx, I have bx equals 2 pi, and so then when I divide both sides by b, I get 2 pi over b being my period. Now, if b is between 0 or 1, meaning like a half or a third or whatever, the period is greater, or the graph's x-intercepts get all stretched further apart. If b is greater than 1, then the period is shortened. My x-intercepts occur at a more frequent interval. Now, if b is negative, then you just have to remember what's up with even and odd functions. Remember, if it's like negative x, it's the same thing as negative sine x, and for cosine it has no effect. And so now let's talk about translations. Translations horizontally are going to be the c, right? Because the same thing with other functions like point slope form or vertex form of a quadratic. If inside the parentheses before I squared, I added or subtracted, I'm going to cause a left or right shift. Same thing here. And we call it a phase shift with trig functions. So it's going to be c over b. And where I get that, I can figure out the left and right endpoints of a cycle by determining bx minus c equals 0 and bx minus c equals 2 pi, because those are the two endpoints of my standard interval for sine and cosine in terms of the period. So if I solve for this, I can figure out how it's going to shift. Now the final thing, and the easiest of them, is the vertical translation. And it's exactly the same thing as it was for every type of function we saw before. If you add or subtract something, it's going to move the function up or down. So if I just add d, positive or negative is going to move it up or down. Now, we like to think of this for trig functions as where it's going to oscillate through. Normally, sine and cosine isolate about the x-axis, but when I add d, what it's going to do is it's going to shift that line either up or down. So then y equals d is going to be the center of the oscillation. Now, of course, with Desmos or a graphing calculator, you can just type one of these things in and figure out how it's going to be different than the parent y equals sine x or y equals cosine x. Let's just use what we know about translations and transformations to figure out how this graph is going to be different and how we can graph it by hand. So first and foremost, most important thing is the amplitude. And I know the amplitude is going to be A, or the thing that's multiplied by the cosine. In this case, it's 3. And then this plus 2 here tells me a shift. So it's going to oscillate about y equals 2 because it's a positive 2. And then I need to figure out my period. And so what I do is I take 2 pi and I divide it by the coefficient of the x in cosine of x, which is 2, or pi. So what this means is the key points I need to find, the maximum, the minimum, and the intercepts, has to be on the interval between 0 and pi. And so then I just have to think about, well, how is that different than normal cosine? Well, it's half the length of normal cosine. And normally cosine has key points at 0, pi over 2, pi, 3 pi over 2, and then 2 pi. But what I'm doing is I'm going to compress these same key points into their interval from 0 to pi. So I need to find what is going on at 0. And instead of pi over 2, I'm looking at half that. So I want to know what's happening at pi over 4. And then I want to know what's happening at pi over 2. And then I want to know what's happening at 3 pi over 4. And then I want to know what's happening at just plain old pi. Because these, remember, are the location of the key points for cosine that has a period of 2 pi. And this function that I'm trying to graph here has a period of 0 to pi, so I had to chop them all in half. And the same kind of key points that I had here at these intervals, I'm going to have on these here. So now I'm going to use a little bit of graphing. So I have a sketch here that I'm going to use to figure out those key points. And I'm not actually going to calculate anything. I'm not going to plug it in. I'm just going to use what I know. And so I know that at y equals 2, I have the line that my function is going to oscillate between. I know the amplitude is 3, so it's going to go up 1, 2, 3 to 5, and it's going to go down 1, 2, 3 to -1. So my max value is going to be 5, and my min value is going to be -1. Now, since it was cosine, it starts off in its maximum up here at 5. And then it's supposed to, at the first key point, pi over 4 in this case, hit, well, what used to be the x-axis, but now the point y equals 2. And then at pi over 2, it hits its minimum over here at -1. And then at 3 pi over 4, it comes back to the line of oscillation. And at pi, it goes back to its maximum. At 0, it's going to be at 5. At pi over 4, it's going to be at 2. At pi over 2, it's going to be at -1. At 3 pi over 4, it's going to go back to 2. And at pi, it's going to go back to 5. So now I know all the key features of the graph.